In the shadowy world of cybersecurity, malware developers craft their creations to be as elusive as possible, and one of their primary strategies involves self-deletion techniques executed right after the payload runs its course. These methods meticulously erase all traces of the malicious file from the system, drastically minimizing the forensic evidence that security analysts and investigators might otherwise use to dissect and attribute the attack. By vanishing without a footprint, the malware avoids prolonged detection and analysis that could lead to countermeasures. Today, we'll delve into the intricacies of how these payloads expertly delete themselves, uncovering the clever mechanisms designed to thwart even the most determined digital forensics efforts. One of the most prevalent and reliable methods employed by malware is to override its own executable file with streams of random, meaningless data multiple times before issuing the final deletion command. This overriding process, often performed in several passes, ensures that the original malicious code is completely supplanted by junk data, rendering any attempt at file recovery utterly futile, even when employing sophisticated forensic tools capable of data carving or magnetic force microscopy. The technique exploits the way data is stored on storage media, overriding not just the file allocation table entries, but the actual data sectors themselves, leaving no recoverable remnants for analysts to reconstruct the malware structure, behavior, or origins. Taking stealth to another level, some malware implements a technique where it first encrypts its own binary using a robust algorithm, transforming the readable code into an indecipherable ciphertext, and then deliberately deletes the decryption key required to reverse the process. Without this key, which might be generated dynamically and immediately shredded or scattered irretrievably, the encrypted file becomes nothing more than a blob of useless, scrambled garbage that defies decryption attempts by security researchers. This approach not only hides the malware during its active phase, but ensures that post-infection forensics yield no actionable intelligence, as the core functionality remains locked away forever. For more advanced persistent threats, process hollowing represents a pinnacle of evasion, where the malware injects its payload into the memory space of a legitimate host process, hollowing out and replacing the original code while masquerading under the trusted process name. Once running entirely in volatile memory, the malware completes its objectives and then systematically wipes its presence from the disk by overwriting and deleting its dropper file, followed by unmapping its code segments from memory, resulting in zero-disk artifacts or running processes for endpoint detection tools to flag. This memory-resident execution model leaves investigators staring at a clean slate, with no binaries to reverse engineer and no behavioral logs pointing back to the intrusion vector. Beyond these core tactics, malware creators incorporate additional layers of obfuscation, such as invoking specialized shredding utilities that overwrite files with predefined patterns like all zeros, all ones, or random data across multiple iterations to defeat advanced recovery software, or configuring scheduled tasks via system APIs to trigger delayed deletions hours or days later when scrutiny might be lower. Gaining a thorough understanding of these self-erasure mechanisms empowers defenders to enhance monitoring for anomalous file operations, memory injections, and task scheduler abuse, ultimately helping to fortify systems against such insidious threats. Stay vigilant, prioritize robust endpoint protection, and keep abreast of evolving malware behaviors to maintain the upper hand in this cat-and-mouse game of cybersecurity.